is a short paper, so I might be a little rushed, so feel free to talk to me offline. So I'm Zhen. Our paper title is A Scalable Approach to Periodical Personalized Recommendations. This is joint work with Ish and John from Ticketmaster Data Science at Hollywood. So we are interested in periodical recommendations, which is pretty popular nowadays. They could be key traffic and conversion driver for many e-commerce websites. Me, myself, get weekly emails from Coursera, Sony, LinkedIn. So at Ticketmaster, our goal is to connect fans with live events in a personalized way, and this is one of our products. So periodical recommendations is pretty challenging. So consider traditional collaborative filtering, and two of the major concerns could be about context and novelty. And these two factors are kind of exaggerated in periodical recommendations. For example, there could be dramatic context change across weeks or months. Also, if we didn't consider novelty, recommending the same stuff or similar stuff across weeks could be a disaster for our users. So there is a family of algorithms called contextual bandits from machine learning that is promising to address both problems. Just by looking at its name, the contextual part takes care of the context problem by using some machine learning model, and the bandits part uses some exploration routines to introduce novelty while trying to learn a better model. There is a large literature here, but basically one major category of contextual bandits algorithm is randomization-based, and they are best suited for online applications with fast feedback loops. But for periodical recommendations, we don't have such fast feedback loops. So the other category, UCB or upper confidence bound type algorithms might be more suitable. So the basic idea here is when we try to predict a utility or score or a probability of clicks or conversions, we derive some kind of confidence interval, and when we make a prediction, we use its upper bound. So the intuition here is basically we try our best with some clue while we do exploration. However, most existing algorithms are slow or difficult to implement, and in this paper, we introduce a new scalable approach that is open source. So when we think about confidence intervals, we think about bootstrapping from Stats 101. So when we have n points of data, we first do sampling with replacement to generate a bunch of new data sets. Then we train a model on each of them, and at prediction time, we have a bunch of predictions, so we can do whatever we want. However, such procedure is difficult for big data problems and is impossible for streaming data with unknown number of n. Then here comes the idea of online bootstrapping. So the key observation here is the number of times that each original data gets selected in a new data set follows a binomial distribution of n, 1 over n. And this distribution converges to a Poisson distribution of rate 1. This is interesting because basically it tells us that we can independently sample the weight of each original data independently, regardless of other data point and regardless of the total number of examples. So this leads to a simple algorithm. So online learning algorithm. So for each example, and for each bootstrap models, we simply sample the example weight from a Poisson distribution of rate 1, and then feed it into some learning algorithm. At prediction time, we can generate the predictions and use its upper bound. So there are two interesting things here. So first, we assume there's some learn function, which we can actually use as a black box. This leads to the idea of learning reductions in machine learning. This actually allows us to use existing efficient implementations or algorithms out there for free. And for this framework, the algorithm needs to be, the learn function needs to be online and weight aware. There are already some pretty good implementations and algorithms out there, and it's still an active research area in machine learning. Another thing to notice is each example is only parsed once and then fed to all the models with different ways. So this largely minimizes I/O, which could be a pain in practice. Okay, we also use some other techniques to make the framework more scalable, and the framework is actually open sourced in a software package called BopperWebit. Many of you might be aware of. So basically, by combining all the techniques we used, we're able to achieve sublinear running time with respect to the number of bootstrapped models. While for traditional bootstrapping, the running time could just explode. Then we do this on offline evaluation using our Ticketmaster weekly email recommendation dataset. And we measure precision at top N, and on the holdout side, we got better results than many existing algorithms. Then we conducted a large-scale real-world evaluation. We did A/B testing for over 1 month on more than 40 million users, and compared with an existing collaborative filtering approach. And we show better results, consistent better results on both conversion and click-through rate. So the keywords for our framework is scalable. It uses several techniques, mainly from machine learning, such as learning reduction, online learning, feature hashing, memory management. And we did both offline and online evaluation, and you can check the code out in BopperWebit. That's it. Thanks.
With a modest little "that's it" at the end after getting people to go download the code. Do we have some questions? If not immediately, then I'm going to take the privilege of jumping in with one. As you went through the timing, obviously, somewhat quickly through the evaluation, I want to understand those improved percentages against collaborative filtering.
Yeah, okay. That's
what are the actual rates that these are based on, and how big a difference actually is this? Is it are we getting 1% and getting it to 1.1, or is this 5% to 5 point?
Yeah, I would say the actual numbers are kind of sensitive, but we show that it's the differences are past the statistical test at a large scale. So.
Can you tell us anything about the domain of the test that's not sensitive?
The domain? Yeah, it's our ticket.
So it's the same domain.
Yeah, it's our real-world Ticketmaster live event recommendation emails.
Yeah. I'm happy to keep going, but if somebody wants to come in there, we can do that. Not that I'm going to ask you one more question about this as you're talking about the sequence. How much of this is dependent on repetitive consumption of what's tagged as the same content? I mean, because it seems like you picked a model that's geared towards what may be repetitive periodic consumption, but it feels like the same technique could work just as well in a domain that doesn't necessarily have repetitive consumption.
Yeah, I think the framework really falls in the contextual bandit framework, and contextual bandit really tries to answer the question of doing both exploitation and exploration, which could also based on some context. So I feel it could be applicable for many real-world applications.
Great. Well, thank you again.
Thank you.